Hi, I'm Fernando Pereira from UFMG in Brazil, and today we shall talk about a dense implementation of the tainted flow analysis. We shall explain how this implementation works using the toy language that we have defined in the last class. Our dense analysis will map every variable at every program point to one of three possible abstract states: tainted, clean, or undefined. A program point, by the way, is any point in between two consecutive instructions. So basically, we'll be working on this lattice. This lattice is formed by sets of pairs. These pairs are formed by a variable and its abstract state. This lattice is actually the product of two lattices. The first contains the variables in the program, here, and the second contains only three elements: tainted, clean, and undefined. Tainted is larger than clean, which is larger than undefined. Notice that when we visualize the product lattice, whenever a variable is undefined, we simply don't write it. Our analysis is dense because we work with the lattice of pairs. Instead of saying that a variable is clean or tainted, we say that a variable is either clean or tainted at a specific program point. So the state of the variable can change depending on which program point we are. Let's see how this analysis works on our example program. We start by mapping every variable to undefined at every program point. That's why we have these maps of variables to question marks everywhere. The question now is how we can iterate the analysis so that we replace these question marks with either a C for clean or a T for tainted. We will use a work list, of course. So we initialize the work list with L0, which is the first instruction in the program. Once we interpret the constraint for L0, we see that it has the effect of changing the state of V in the next program point. That changes the input of L1, the next label, and we add it to the work list. When we interpret L1 abstractly, we change the input of L2, and so we add L2 to the work list. Notice that L1 is a filter, so X will be clean. Next thing, we interpret the validate instruction. That gives us that V will be clean when validates true, that is in L3, and will be tainted when it's false, that is in L9. We add these two instructions, L3 and L9, to the work list. We interpret the branch at L3. The branch does not have any effect. It's like a trivial transfer function. It only copies the input to the output. But this function does change the inputs of L4 and L8, and we add both to the working list. We interpret the branch at L9, and it changes the input to itself. So we add it back in the work list. When we interpret L4, we change the input of L5, and so we add L5 to the work list. Notice that L4 is async. It's also a trivial transfer function. What enters becomes what goes out. When we interpret L8, we change another input of L9. We had already seen L9 before, but the change in the edge L8 to L9 forces us to add L9 back to the work list. Notice that now we have information colliding. We have data coming from two edges and reaching L9. In this case, what happens? Would you like to think about it? We have to look into the lattice. We have this table to define the join operator. So if tainted collides with clean, the result's tainted, for instance. In this case, we have V as clean coming from L8 and V as tainted coming from L2. The result's tainted, V in the output of L9. But V was already tainted, so nothing changes, and we don't have to put L9 back in the work list. When we interpret L5, we see that X becomes tainted, because L5 is reading from the source and assigning to X, so we put L6 into the work list. L6 yields V clean and X tainted in the input of L7, and L7 goes into the work list. L7 is a branch, so it's a trivial transfer function that just copies the input into the output, and L3 goes to the work list. Now we have information colliding at L3. Would you like to stop the video and tell me what would happen? Well, we have X becoming tainted because it's tainted at L7, and we need to add L4 and L8 to the work list because their inputs have changed. And then we see that X arrived at L4 as tainted. That's a security vulnerability because L4 is writing X to a sensitive site, so we report that this program contains a security vulnerability. We will still need to add L5 to the work list. Once we interpret L8, nothing changes, so we do not add anything to the work list. We take L5 from the work list and nothing changes, so nothing is put back into the work list. Now there is only one node in the work list. We take it out, and then we see that X becomes tainted in the output of L9. We put L9 back in the work list. Now, once we evaluate L9 again, nothing changes this time, and we are done. The work list is empty, and the analysis is over. The system of constraints has stabilized. I have 2 questions to you before we are done for good. Can you think about them? That's a good time to stop the video, read, and answer the questions. For the first question, the answer is yes. The lattice is finite, and the transfer functions are monotonic. You see, once an undefined variable becomes clean, it never becomes undefined again. And once a clean variable becomes tainted, it will never become clean again. Now, about the last question, what's the complexity of this algorithm? You might think that the algorithm runs in time proportional to the number of variables times the number of program points. That's almost true. We need to consider that we need to produce the join of abstract states too. So whenever we have vectors of variables colliding, we need to find the resulting vector. This operation is proportional to the size of the vectors, but because the number of predecessors of a node is small, usually we can do this in constant time. And the number of program points is roughly equivalent to the number of variables, so in the end the algorithm is quadratic on the number of variables. And that's it for our dense analysis. Next class we shall talk about the sparse implementation.